Hey, Chemistry 12 class, Mr. Lum here again, and we're going to be taking a look at our 4.5 worksheet that goes along with our Chem 12 4.5 lecture video, and this will hopefully prepare you for your 4.5 Chemistry 12 quiz. Anyways, so one thing that I want to make sure that you have is you have your data booklet. So I got mine right here on relative strengths of Bronsted-Lowry acids and bases. If you don't know where this is, you can find this in, you can message me, or you can find this on our Microsoft Teams under the documents and stuff like that. Now, so first off, we're going to go through this and take a look at some of these questions. So the first one says, what would have the higher H3O concentration in water? HClO4 or HNO2? So we have the same molarity. So that's important. So we have the same molarity. Now, if you remember from the lesson, acids will go from, so we'll just take an example like HClO4 plus water. This hydrogen right here will break off and it'll attach to the H2O and turn into H3O plus. And then you'll just have ClO4, a little messy, ClO4 minus. And so not all of the H's will break off of the this HClO4. So only some of them will, and it'll actually form an equilibrium. And so which one will have the highest concentration of this? So we can't tell from looking at right here, but what we can tell is we can look by right here. So first off, we see that HClO4 is right here. Okay, and the other one was HNO2. Now, HNO2, nitrous acid, is a weak acid. It'll form an equilibrium. This one will actually not form an equilibrium. See, this one does. And we can tell because it has a Ka that's very, very large. So when I wrote that this will form an equilibrium, I somewhat lied. It doesn't form an equilibrium. It just goes one way. So if you had 10 molar HClO4, what would the concentration of H3O plus be? Well, this one would have actually 10 molar H3O plus. This one would have a very small H3O plus concentration. And we can calculate this, but we'll learn that later. But this one will have all of this will turn to H3O plus. So which one would have a higher concentration? Well, it'd just be this one right here. Right? The other way you can tell is like which one has a higher Ka value. This has a very high Ka value. This has a very low Ka value, 10 to the negative fourth. So the one with a higher Ka value will always make a higher H3O plus concentrations. So the answer is just HClO4. It's a strong acid. Okay, it's not even a competition. What would have a higher H3O plus, HiO3 or H2SO3? So HiO3 right here or H2SO3. Well, which one has a higher Ka value? Well, this one right here. Okay, so since it has a higher number, a larger number, it makes more H3O plus. So HiO3. Okay. Now, please remember for this idea right here, and we'll learn about something else later, this only is true when you have equal concentrations. If I said 1 molar of this and 3 molar of that of H2SO3, you would have to calculate it out, okay? But we'll learn more about that in the future. So the next one right here, NH4 and HF, same thing. We see HF right here. We see NH4 way down here. So HF. Okay, again, same concentration, so we know that's HF. And the idea for these first three questions is just using the table. Yeah, actually for the first like 9 questions, just using the table. Now, difficult question, HSO3 or HC2O4 minus, and we're looking for the stronger acid. So it says stronger acid. We can see later on it'll say stronger base, and we'll get to that one. But this one says stronger acid. So HSO3 and HC2O4. So HSO3, and what we see here, this is the confusing one. We see an HSO3 right here, but this is on the base side right here. So we cannot look at that one. That is on the base side. We're looking at comparing the acids. So we have to find the HSO3 on the acid side, which is right there. So here we find HSO3 on the acid side. Okay, so that one right there. And I can't remember our other one that we have to look up. HC2O4 minus. So HC2O4 minus. Here it is, right there. Okay, so we have to compare this one and this one. Well, this one's higher up, so this is the stronger acid. So hydrogen oxalate ion, this one, okay? That one. HSO3 or HSO4 minus. I'm just going to quickly erase some of this stuff because it's getting a little bit crowded. So HSO3 or HSO4 minus. So again, HSO3 right here, but we're looking for acids. So we have to look for HSO3 minus right there. And we have to look for HSO4 minus. And having some difficulties finding it. I'm sure that you were like, there it is, I see it. Oh, there it is, I see it now. HSO4 minus. So here are our two right here, HSO4 minus and HSO3 minus. And we see HSO4 minus is way higher. So we're going to say HSO4 minus. That's our answer. HPO4, HSO3. HPO4. Just going to erase some of this stuff again. HPO4 right there. And what was the other one? HPO4 and HSO3. And we just did that one, of course. So here it is. So HSO3 is higher. Okay. Oops. Wrong one. HSO3 is higher. So that one. Now, here's the next one right here. It says the stronger base. And it says HPO4 and HSO3. And a lot of people are just going to circle this one right away. But let's take a look first. So we're at HPO4 and HSO3 minus. So first, we're going to pull this thing up. We're going to erase all this stuff out. Okay. Now, we want to say this HPO4. Now, that's not the HPO4 we're looking for. We're looking for the base. So here's HPO4. That is where, because it's on the base side. Now we have to find HSO3 on the base side. And there it is way up there. Now, if we look right here, strength of the base, the further you go down is stronger. Okay, so HPO4 2 minus is stronger than HSO3. This one's very, very weak. Okay, and these ones up here are not even considered bases because they cannot be. Now, anyways, so HPO4 is a stronger base. HPO4 2 minus. So HSO3 or HSO4. Okay. So we have HSO3 and we're looking for HSO4 minus. So here's HSO4 minus. Now here is the thing. This is a little bit confusing. So we have right there, which one is a weaker base or a stronger base? So we have HSO3 this is going to be the stronger one because this one right here. So first I'm going to write the answer, HSO3 minus. HSO4 not a base. Okay. And this is going to be a little bit tricky, but I'm going to show you why HSO4 minus is not a base. So right here, HSO4 cannot be a base because if it was HSO4 minus plus H2O, you're saying that it would turn into OH minus plus H2SO4. This reaction is impossible. It cannot happen. You cannot put HSO4 minus plus H2O and makes a strong acid. So if you have, if it makes a strong acid, well, this will be in water. It'll turn right back into HSO4. This reaction cannot happen. You cannot make H2SO4 from HSO4 by throwing it into water. So it's not actually going to be a base at all. So that one's not a base. Now, next one we have HCO3 and HCOO minus. So we have, I'm going to put the highlighter on, HCO3. And I think we're looking at HCO minus, if I'm remembering correct. HCO minus and HCO3. So we found HCO minus. Let's find HCO3. There it is. Okay. So stronger base further down. So it's carbonic or HCO3, hydrogen carbonate. Oops. There. Okay. So the idea for the first 9 questions is to help you get used to using that table. Okay. So now that we found the table, we can kind of figure a few things out. Okay. Now, the next thing right now is we're going to classify each of the following as a strong acid, weak acid, strong base, weak base, or a spectator ion. Okay. Now, so a lot of these ones I have kind of memorized, but we'll go over them because you probably don't have this thing memorized like I do. So it's going to be a little bit slow, but that's fine. Okay, so we're just going to kind of clean this up just a bit right here. And yeah, so the first one that we're going to do is F minus right here. So you just look up F minus, and what we find here is that we found F minus to be right here. Oops, let me put my pen on. F minus is right there. It is on the base side, okay, has a number associated with it, so therefore it's a weak base. Weak base. Now I'm going to jump over to Cl minus because I think this has a good contrast to this. So Cl minus is right up here. It does not have a number associated with it. HCl turns into H plus and Cl minus. This is a one-way kind of reaction. It's not an equilibrium. So Cl minus is actually a spectator ion. It is not going to be a base. So we'd say spectator ion. Okay. We're going to take a look at the next one right here, HIO3. So we see HiO3 right here, very clearly weak acid. Weak acid. NH3 also very clearly right here, number associated with it, weak base. Okay. Actually, you know what I'm going to do? That'll make it better. Okay. NO3 minus, same thing as before. It's right up here. It's a strong. This HNO3 is a strong acid, so this is just going to be a spectator ion. Okay. O2 minus, kind of crazy, and we'll talk more about this one later. But this is going to be your strong base. Okay. HClO4. Oops, too far. Up here. Strong acid. CH3, COOH. Right here. Weak acid. C2O4. C2O4. Weak base. We're so used to seeing that OH is the base, but that is kind of the Arrhenius definition of what an acid and a base is. Now we're talking about Bronsted-Lowry definition of what an acid and base is. So C2O4, yeah, it doesn't have the OH there, but it will accept protons, and that makes it a base. So since it doesn't fully ionize, it's weak. Okay, ClO4 is right there. That's a spectator. Okay, so again, this question is kind of just like helping us understand how to use this table and where things are on it. Okay, the first calculation, what is the H3O plus concentration of 2 moles of nitric acid? So here's nitric acid. So this is 100% ionization. So if you started with HNO3, sorry, I should kind of do it properly and say plus water. It's not going to be an equilibrium. It's just going to go a one-way reaction and turn into H3O plus and NO3 minus. So if we started with 0.02 moles, moles of this, we would, since it's 100% going and it's a 1-to-1-to-1 ratio, we would end up with 0.020 moles of this and 0.020 moles of this. We want to find the concentration of this thing right here. So I'm just going to simply go 0.020 moles divided by our liters, 500 mils, or in other words, 0.5000 liters. And I have my calculator here. 0.02 divided by 0.5 equals 0.04. Now that I think about it, I didn't need a calculator. 0.04 0 molarity. Okay. Now, if I asked the same question and I said, what is the H3O plus concentration of H2SO3, then we'd be looking at a much different calculation. We'd be looking at like ice tables and all that kind of stuff. Okay. But we're going to get that in the future. Okay. Next question. What is the Ka expression of HF in water? So first I'm going to write my formula. HF plus water turns into H3O plus F minus. If you ever wonder, technically these all give you the Ka expressions on this thing right here. So here's our thing right here. Now it doesn't have the water in there, and I'll show you a little thing in a little bit. But our Ka, it does tell us the Ka, but we want the expression. So just products over reactants. So H3O plus times concentration of F minus over concentration of HF. That's it right there. Now, if you wanted to be lazy and not do this whole thing right here, so sorry, let me just back up. This is our answer right here. But if you want to be lazy and not do this whole big calculation and the formula and all that kind of stuff, technically this is your Ka expression right here. You can, if you wrote this on a test, or this would be perfectly fine. Ka equals, and I'm just going to take the products of this thing over the reactants. So if I just wrote down H plus times F minus over HF, these things are the same thing. H3O and H plus, there's no difference really. So if you wrote this one, or if you wrote this one, I would mark both completely right. And sometimes you'll even see me kind of switch between those two. Now, what is the Kb expression? I know we didn't learn about Kb, but we're going to take a quick little peek into it right now. So first off, I'm going to write a formula. So on the lecture, you should have seen me write something like F minus plus H2O. Now, for these ones, you must write the H2O. It won't work if you don't. F minus plus H2O forms an equilibrium, so we write the equilibrium side. All bases will make OH minus in water. That's what a base is. And then that H, one of those H's was taken off and placed onto that F, so it'll be making HF right there. So again, expressions, now hopefully you figured out Kb just means is like Ka, but the constant for the base, and so it's just products over reactants. So Kb is products over reactants. So in other words, concentration of OH minus times the concentration of HF over, water is liquid, so we don't put that in there, over the concentration of F minus. Okay. For acid and base stuff, this is a little bit of a cheat. This is something that's just something that you should know, I guess. But we should never have any squares or anything like that in there, because we're kind of doing like the simple stuff in here. If we're dealing with some different types of acids, we might see a squared or something like that. Now, remember, we did KEQs, things would be to the power of 2, things would be power of 3. But for Ka, in this course, we're not going to come across any of those kinds of things. So anyways, here is our Kb expression, and we're going to be talking more about Kb in the future. Anyways, that is your video answer guide. Hope it helps. If you don't understand what I'm talking about here, give me a message, and we'll try to set up some kind of online class, and I can help you through it. Okay?